Okay, this is meen415 heat flow lab. I'm going to talk about the lab number 5, original number 5, but actually the fourth lab you're going to do. Okay, so let me turn on share my screen with the lab handout. I posted the lab handout on Moodle. Okay, so this is the second lab of the cross-flow heat exchanger. Okay, here a list of those equations. The one thing I want to mention here is here in this lab we are going to use the heat flux instead of the heat transfer rate. Okay, so the same thing. Heat transfer rate is HA delta T, right? H is also heat transfer rate is same as the power, electrical power generated by the electrical heater, V squared over R, right? So heat flux is heat transfer rate divided by area, the surface area of the fin, of the finger tube. This is the second level of the heat cross-flow heat exchanger. We're going to use the finger tube. Last time we do the smooth tube, right? So that's the difference here. So basically heat flux is heat transfer rate per area. So the equation in terms of heat flux will be H delta T, T surface minus T ambient, right? Okay, rest of the equation are the same. Okay, so let me show you the layout, the experiment. Now you see here, last time remember we have one smooth fin. Oh, I'm sorry, one smooth tube heated unit inside the cross-flow heat exchanger, right? Now we have a finger tube bundle. Okay, so many of them, many finger tubes, but the unit are the 4. Okay, actually there's only one active unit for measurement. Okay, see this one connected to the monitor, to the heater. So this unit is heated. Okay, so but these 3 are dummy units. So basically you can put the dummy unit out and place the active unit inside this position. So these 4 positions, we can put the active unit there, okay, to measure. So in that sense, we can measure the position effect, okay, on heat transfer in this finger tube bundle, okay. So in this lab, we are going to, you're going to turn on the fan. The blower, we are not changing the flow speed. We just turn on the blower to the maximum wind. Okay, so we don't, not like last time we changed the speed and changed the Reynolds number. We want to see the Nusselt number versus Reynolds number, right? That's a previous lab. Here we're not looking at that. We're just looking at, try to find the relationship between the heat flux and the temperature difference. Okay, to show actually the slope, and the slope indicates the heat transfer coefficient, right? So also we are going to test all 4 positions. The heat transfer, the heat flux change a little bit at the 4 different positions. Okay, the reason is obviously the wind blows from the bottom to the top, right? So when wind goes through, the contact area to the wing is different. Okay, in the front, this one, the bottom one, you see a lot of frontal areas to face the wing. But for the middle units, you don't have that much of the frontal area. But the wing actually goes through the bundle because area getting smaller. So it's squeezed, the velocity increased, okay, in between. So it might give a positive effect in heat transfer, okay. The last one, you will see that a lot of area in the back, but I don't know how much of the benefiting the heat transfer because wing is from the bottom to the top. So we want to see that the position effect on heat transfer, okay. So these are the dimensions, everything, the constants that you need for the calculation. Okay, let's look at the outcome and the reporting. So plot the relation between the heat flux and the temperature difference, Ts and the Ta. So in a sense, you will have a plot. Okay, vertical axis will be, okay, let me draw it on. Let me switch my screen. Let me draw on the whiteboard. Okay. So I want you to produce a plot like this. This is delta T, and this is heat flux. So heat flux is H times T surface minus T infinite, or T ambient, TA, right? So basically that's the relationship. This is the slope, right? So this is the delta T. Okay, so you will pick 4 different delta T's. It's easy, right? T infinite, ambient temperature doesn't change in there, all right? So you can switch the voltage to change the surface temperature. Therefore, you will have different delta T's, okay? So you increase the voltage, the surface temperature will be higher. Since this time you don't change the wind speed, okay? The flow is the same. So when you increase the voltage, you will increase the surface temperature, okay? So you will have, let's say, 4 delta T's. Each delta T, you will need to measure a heat flux. Remember, heat flux is just the heat transfer rate. Heat transfer rate is from the voltage times, voltage squared divided by resistance, right? Same as last time. So heat flux is just the heat transfer rate divided by area. Surface area is given, okay, in the handout. So you should be able to easily calculate that. So you will have a straight line like this, okay? So it should be linear, okay, for each position. So each position you should have a plot, a curve, a straight line. So I don't know the order, okay? So you have 4 lines representing 4 positions, okay? On each position, you will measure 4 delta T's. You will set 4 delta T, and therefore you will measure 4 different heat transfer rate, heat flux, okay? So actually, if you do the experiment, there will be total 16 measurements. 16 measurements. For each position, you set 4 different temperatures, okay? So you 4 different heat flux. So 4 position, 4 times 4 is 16, okay? 16 measurement, so produce. So in that sense, the top one is the best heat transfer, right? Okay, and the slope also, if it's bigger, then the heat transfer coefficient H is bigger. So that can indicate the difference in heat transfer in the 4 positions. Okay, I also want you to compare. That one is a smooth tube, okay? Obviously, your heat transfer for the finger tube, these 4 are finger tube. Thin tube should be better than the smooth tube, obviously, common sense, okay? So I want you to show, actually, the smooth tube curve is much lower than the 4 finger tube. So how do you determine the smooth tube? Smooth tube data, you can get it from last lab, okay? You have 2 correlations to compare, right? You remember Nusselt number last time is Nusselt number versus Reynolds number. Reynolds number is from the flow rate, from the wind speed. So for this wind speed, for the wind speed in this new lab, you can calculate a Reynolds number, okay? So for the smooth tube, it's like this, right? Nusselt number versus Reynolds number. So if you calculate that Reynolds number, then you should be able to get a Nusselt number for this Reynolds number. Nusselt number is just dimensional heat transfer coefficient. So you can calculate H, okay, for the smooth tube based on last time's correlation or based on last time's result. So you can find the H for the smooth tube. So you substitute into this equation with the same 4 delta T with a given H for the smooth tube, you should be able to calculate 4 different heat flux, okay? In order to, therefore you can generate that line for the smooth tube, okay? So the smooth tube is from the calculation from this equation, okay? Based on the H you measured the last time, okay? So maybe depend on the wind speed might be smaller, okay? Then you use correlation. The correlation covers very wide Reynolds number range. Your measurement only a portion of Reynolds number, right? Last time, maybe it's out. Okay, it's okay. So you can use that correlation. The two correlation, whichever you want to use, doesn't matter. One is longer than the other, I remember. You can pick one, okay? Calculate your Reynolds number based on the wind speed for the new lab. Then you should be able to find the Nusselt number. Then you should be able to find H. Then you should be able to find the heat flux, okay, for the smooth tube or for feed. The heat flux is based on the for the 4 delta T's you use, okay. So this is this lab. So this is the result I expect to see, okay. So I guess let me know if you have any questions. I don't have the experiment video, so this video is for your guidance. It's a lecture, okay. I will, and you know now you know what the apparatus looks like. I show you the picture. So I will give you the measurement data. I will post it in our GroupMe group, okay. So watch this video, then use the data I provide you to do the calculation and produce a report, just like the previous lab. Okay. Okay, that's it.